We are looking at an ideal Rankine cycle, okay, consisting of these four components. We have been provided information about the state at the entrance to the turbine with the state 1, right? The pressure is given. It's mentioned that it's saturated vapor. Same way information about state 3 is given. And it's an ideal Rankine cycle. So we know that the process 1 or 2, which is the expansion within the turbine, it's isentropic. Same way, the compression within the pump is also isentropic. So we know the entropies at state 4 and state 2 simply because we know the entropies at state 1 and 3. All right, so that's enough information for us to go ahead and solve this problem. The other thing that's mentioned is the net power output of the cycle. It's given as 100 megawatt. And for the cycle, we need to determine the thermal efficiency, backwork ratio, mass flow rate of the steam in kilogram per hour, and the thermal efficiency. Now, the first three parts are something that's there in the textbook. The part D is something that I added just to give you a better understanding of how this efficiency business works. All right, so let's look at what we did. Certainly, when you're provided with this sort of a question where you need to go and determine the efficiency, or let's even the work output or heat input or anything like that, you're going to need enthalpies, right? So, I mean, we need the values for enthalpies to even go ahead solving this problem. And that's what we spent time on Sunday. We looked at how to find different states and then basically get the enthalpies at different states. So enthalpies at state 1 and 3 were very straightforward, right? These are simply Hg at this pressure and Hf at the condenser pressure. And for the other two enthalpies, which is H2 and H4, we had to make use of the fact that the process is isentropic. So we found out the quality for state 2 and then the enthalpy. And similarly for H4, we had to sort of make use of the fact that since it's an isentropic process, it's also a reversible process or an internally reversible process. So we made use of the work input formula for an open system, right? The reversible work input formula, and we equated this to the pump work input, which is basically equal to the difference in the enthalpies. And this is how we found. Okay, so this is a very simple trick that we need to determine H4. It is something that I like to ask in one of the class tests or in quizzes. So make sure you are aware about how to get this pump work input or the enthalpy at state 4. All right. So once all the enthalpies are known, determining or calculating thermal efficiency is rather simple thing, right? It's not a very difficult task now. Thermal efficiency, as we know, is simply a ratio of the net work output of the cycle divided by the heat input of the cycle. Now, when we talk about the net work output, well, we are producing some work output in the turbine, certainly. There's some work out happening, but we need to provide some work input to the pump, right? To pump the work, to pump the liquid, or to pump the water from a pressure of 0.08 bar or 0.008 MPa to 80 bar. Okay, we need to pressurize it. So we need to consider the work input that we need to provide in the pump, and therefore we take the turbine work output minus pump work input divided by the heat input, and that's what gives you the thermal efficiency, right? And we have all the enthalpies here, H1 to H4, and you plug in the numbers. Okay, these are again the only thing here was to determine these enthalpies, right? Once you plug in the numbers, we get an efficiency of 37.1%. Now, considering that most of the practical power plants have efficiency somewhere in the range of 45%, an efficiency of 37% is not a bad efficiency. It's sort of an average thing. Yes, it can be improved, but it's sort of okay. But one thing to consider here is that we're getting a 37.1% efficiency for an ideal Rankine cycle. Okay, we are considering the processes to be isentropic, the expansion and the compression. So this is not always the case. So we'll have to see how we can play around with this number. But for now, 37 is not bad. And this figure simply tells you that out of the heat that we are providing, right, it's telling you how much work we are able to extract out of it. So out of a certain amount of heat input that comes in the process 1 to 4, 37.1 is basically the net work output, right? So turbine work out minus pump work in. So this is reasonable. Okay, reasonably good. And now you may ask what's happening with the rest. Well, the rest is simply being rejected, right, to the surroundings. It's going as q dot out. So this is what's happening in here. All right. So this is the first part is done. Now for the second part, the backwork ratio. This is another thing which is very useful. The backwork ratio is simply the ratio of pump work input divided by the turbine work output. We're always interested to calculate this because we want to minimize this as much as possible, right? You want to ensure that you're able to, extract as much work, net work from the given power cycle as much as possible. So you want to minimize pump work as much as possible, and you want this ratio to be as small as possible. If backwork ratio is very much smaller than 1, that's very good for us. Okay, and we would want to keep it that way. Now here when we plug in the numbers for the work input to the pump divided by the work output from the turbine, these are simply the enthalpies that we already calculated or found from the tables. The backwork ratio comes out to be 0.84%, like which is less than 1%. Okay, so this is excellent, and this is the case for all vapor power cycles, right? In all vapor power cycles, the work input to compress a liquid, it's pretty small as compared to the work output we get from the turbine. So this is the usual case, and this is one of the reasons why vapor power cycles make a lot of sense. That's why a lot of systems, whether solar thermal, whether it's nuclear, whatever fuel you use to heat up the working fluid, a lot of these systems depend on the Rankine power cycle to generate power, simply because it makes sense from the backwork ratio point of view. Remember, this backwork ratio of 1% or less than 1% is not always going to be the case for all cycles. When we will go to the Brayton cycle where you have to compress a gas, you will see that this ratio is about 40% or higher. So it varies from cycle to cycle, right? It depends on what you're doing with the working fluid. But whenever we consider a Rankine cycle or a cycle where you're having where you're compressing a liquid, this ratio is going to be pretty small, and this is one of the advantages of this sort of a cycle. All right, so these two are pretty straightforward. These two are things that we have done before. Now let's move forward and calculate the mass flow rate of the steam. We have been provided the net power output. Okay, it's 100 megawatt. So the question is, how do we go ahead and calculate the mass flow rate? Anyone can give me suggestions?
Energy balance equation.
Okay, so you want me to do energy balance for the entire cycle, or how should we go about it?
Yes, I think.
Okay. Yes, we can do sort of energy balance for the entire cycle, but what we're going to get is, heat in plus work in is equal to heat out plus work out. And well, I know all these numbers per unit mass. I just don't know the mass flow rate. I mean, I could just write it as q dot n by m dot plus blah blah blah, because we don't have the mass flow rate yet, so we can't exactly find q dot n. We can find q dot n by m because it's simply equal to h1 minus h4. So yes, that's a good idea usually, but here it's not going to take us far. Any other suggestions? The network output is given to us, right? What we have calculated till now are turbine work output per unit mass, pump work input per unit mass. It's not very complicated. Well, there's a lot of quietness in the room. So are you guys studying for the quiz, or what's the case? You should have some ideas, right? I mean, I'm perfectly fine if the answer is wrong. It's not, the purpose is to have a discussion here, not just to give right answers, because if you know everything, then we don't need to teach this course, right?
Actually,
Yeah.
Doctor, my mind is busy in the quiz.
Okay. Well, maybe then I should have the quiz in the beginning of the class next time.
It's better, Doctor.
It will be
Okay.
safe, doctor.
Uh, all right, we will do that. The problem, the reason I don't have it in the absolute beginning is because some people will join 1 or 2 minutes late and then they'll complain, oh, I did not have enough time. So, all right, we'll do a poll and we'll move it if that is what you guys want. Because yes, I understand that the quiz will always be on your mind till you actually do it and get whatever marks you have to get. All right, let's try to focus here and try to look at this because your preparation is not going to change in the next 20 minutes. Okay, so we just need to get the mass flow rate. All right, and the turbine work output per unit mass is simply the difference in the enthalpies, which we already calculated. Same way with the pump. Now, when we say the net work output, it's simply the turbine work output minus the pump work input. All right. So you could write it as m dot times Wt by m dot or minus Wp by m dot, right? Or I mean, this is one way of writing it, or you could just write the work output of the turbine as mass flow rate times H1 minus H2. Okay, same way you could write it for the pump. The key point is that we know this value of net work output. We know these numbers, the work output per unit mass from the pump, which is equal to this difference in the enthalpies, work input per unit mass in the work output per unit mass from the turbine, which is these difference in enthalpies. Same way we know the work input per unit mass in the pump, right? So you just have to sort of divide that. So m dot would simply be the net work output divided by H1 minus H2 minus H4 minus H3. The enthalpy changes within the turbine and within the pump or the compressor. Okay, so it was very simple. It's not very complicated. You just have to know that this m dot here. We just need to determine it. Okay, that's all we're looking for. So we have these different enthalpies from H1 to H4. The net power output is given. It's a matter of plugging in the numbers here. Now this net power output, it was given in megawatt, right? So we need to convert that into kilowatt before we can calculate the mass flow rate, right? Because everything here in terms of enthalpies is in terms of kilojoule per kilogram. So we need to keep the units consistent. Once you do that, this is the mass flow rate that comes out, about 105 kilogram per second. Now I want you to wait for a minute and sit on this number, right? Think about this. 105 kilogram per second, right? So for water, I mean, if it's sort of difficult to think about kilogram, you say 1 kilogram is about the same as 1 liter of water. Okay, so we need to pump about 100 liters of water every second. All right, this is what's needed to keep the power plant running. So this is a pretty huge quantity of water that we're talking about, right? So if you think about the 1 liter, sorry, if you think about the water bottle that you get in the supermarket for a real, that's about half a liter, right? 0.5 liters. So you're talking about 200 of such bottles, and so much water needs to be supplied every second. So we're talking about absolutely huge quantities of water. Okay, and this again is not any sort of a random number. This is very close to the flow rates that happens in actual power plants. So if you go to the steam power plants in Jeddah or even the steam power plants that are located in the eastern province, you will see that the flow rates are somewhere in this range. Not exactly 105, but could be maybe 90, could be 120, somewhere in this range, right? So this is a very it's very close to the real numbers that we are dealing with. So in the question, we had to provide the mass flow rate in terms of kilogram per hour. So you just need to multiply by 3,600 to do that, and this is the final quantity that we're talking about. It's absolutely a huge quantity that you're dealing with, right? So it's 3.77 into 10 power 5 liters per hour. So you have to sort of pump in a huge amount of water continuously, and you need to circulate that to generate 100 megawatt power output in this particular case, right? For the temperatures given. So here is where this problem mostly ends. You get the mass flow rate, thermal efficiency in Backwork ratio, and you have solved more of it. And if you look at what was asked, the tricky part here was only to get H2 and H4. I would say not the tricky, maybe the slightly involved part. Everything else was very straightforward. Okay, everything else was just a matter of putting in either from the energy balance or using the definitions for enthalpies and Backwork ratio. Now, we calculated the thermal efficiency of this plant to be 37.1%, but I mean, just relying on energy efficiency is not enough. We need to sort of compare it with the situation for a reversible cycle, because just looking at 37.1, it looks like a low efficiency, right? It doesn't look very good. It looks as though we are wasting the remaining 63%, and it's just going to the environment, which is sort of a waste of exergy, right? So before we come to a more, before we decide whether we can make what changes we need to make to, sort of make this power plant more efficient, it's a good idea to sort of calculate the Carnot efficiency, right? Because Carnot efficiency would be the maximum efficiency for the temperature limits that we're looking at. So when we talk about part D, here we need to calculate the thermal efficiency of a Carnot cycle, which operates between the same temperature limits. So what are the temperature limits that we're looking at? We're looking at this, the Tsat here, okay? This Tsat to be the TH, right? In the boiler, Tsat at the boiler pressure. And we're looking at Tsat at the condenser pressure to be the lower temperature, right? Temperature of the low temperature reservoir. So once we get that from the property table, simply by going to the saturated pressure tables and getting up the values for 0.08 bar and 80 bar, we can plug it into this equation. This is the formula for Carnot efficiency, 1 minus T low by T hot. So at 0.08 bar, 41.5 degrees Celsius is the saturation temperature, and at 80 bar, 295 degrees Celsius is the saturation temperature. Now 295 is sort of reasonably hot. It's not very hot. You could go higher than that, but this is what we have for this particular case. Okay, and as you know, we need to convert the degrees Celsius into Kelvin, so we have this plus 273 here, and when we do the calculation, the Carnot efficiency comes out to be 44.6%. Now this is interesting, right? I mean, this tells you that even if you had the most perfect cycle ever, the efficiency would only be 44.6, or let's say 45%, which again is not so nice, right? I mean, you're talking about wasting 55% of the energy, even in the most ideal scenario. So